Number 3 is going to be very similar to what we've just done. What we're trying to do, of course, is we're trying to make this reaction given reactions 1, 2, and 3. So what we're going to do is look at where the compounds are first and see if we need to flip them. Again, where my eyes go is the biggest of the compounds, which is C2H5OH. I notice it's here on the left side. So we're going to have to flip number 1. Let's go ahead and do that now. So I'm going to go ahead and write my products on the left side, 2CO2 plus 2H2O. Then what's on the left, now on the right, C2H5OH plus 2O2. I'm going to go ahead and cross this off. That way I don't make the same mistake again. That way I don't look at this because, again, I need to ignore this reaction now that we flipped it. And because we flipped it, of course, we need to flip the sign. It was a negative. Now it needs to be a positive. All right. So my C2H5OH is now on the right side. So that looks pretty good to me. And there's one of those. So that looks pretty good. Looking at reaction number 2, what I see is this is on the left side. This is on the left side. So that looks pretty good to me. Don't think we need to flip number 2. Reaction number 3, looking at those two. Again, let's see. Water, H2, and half an oxygen. So those, again, are kind of like that. So that looks pretty good. I think everything's going to work out all right. But what we need, again, is it to match exactly. So if we look at reactions 1, 2, and 3, we have 2 CO2. Here we only have 1 CO2 on the right side. Here we have 2 on the left. So my hunch is we're going to have to multiply reaction 2 by 2. Why do I also know that? Is because this here, we have 1 carbon, but we need 2 carbons. So that is for 2 reasons. I now know we need to multiply everything here by 2, which means we multiply this by 2. Okay, so that should work out pretty well. Looking at reaction number 3, I notice I have 2 H2s. I only have 1 here. So that, again, is a clue. I might have to double reaction number 3 as well. Looking at that again, what we have here is, let's see, half an oxygen. We need 1 oxygen. We only have half an oxygen. So yeah, that's probably going to have to be doubled as well. So let's go ahead and do that. So I'm going to double that, double this, so that becomes 1, and double that, so I'm going to have to double this. Okay. All right, let's go ahead and put all of this into one massive equation down here. So again, I'm going to start with the left side, 2 CO2 from reaction 1. I'm going to add to that our 2 waters. So this has now been used. This has now been used. I'm going to go on to reaction number 2 now. 2 carbons plus 2 oxygens. So that's been used. That's been used. I have 2 H2 and another oxygen from reaction 3. So that's used and that's used. Now let's go to the right side of the arrows from reaction 1. C2H5OH plus our 2 oxygens there. So that's used. This is used. Now I'm going to go ahead and go to reaction 2. 2 carbon dioxides, and we have, last but not least, 2 waters. So everything is in the right place. Let's see if anything cancels out. I have 2 CO2s, that cancels. I have 2 waters here and 2 waters there, that cancels. I have 2 oxygens here, I have 2 oxygens there, that cancels. Nothing else does. So when we're done, we're going to have 2 C's plus 2 hydrogens plus 1 oxygen yields C2H5OH. Does that match this? I sure hope so. And it does. Remember, my reactants do not match exactly the order, but as long as they're on the left side, it doesn't make any difference. So we have done it correctly. So what we're going to do now is, of course, this is going to be times 1. I'm going to go ahead and just add them all together. Just do it with parentheses to make this a little bit easier for myself. So I'm going to add positive 875 plus, or excuse me, plus parentheses negative 394.51 times 2, close parentheses, plus open parentheses, negative 285.8 times 2, close parentheses, equals, my final answer is negative 485.62 kilojoules. There we go. That is the total amount of energy change from the top reaction circled in black that is comprised by the 3 reactions in blue. Again, that is called Hess's law. It's the summation of heat change from multiple individual reactions, which can be added up to equal the total enthalpy change or change in heat. There you go, guys. There's our examples. Thank you, guys.